Okay, ready, Erik?
As ready as I'll ever be.
Okay, so hi everybody, and welcome. My name is Liron, and we're going to talk about analytic functions today. So let's start by introducing ourselves. And on this slide and then the last slide, you have all the contact information for me and Erik. So feel free to reach out, follow us. I've got LinkedIn as well. It's not here, but it's quite easy to find me there. Cool. So let's start. As I said, I'm Liron, and if you joined a few minutes ago, you heard that it's 8 a.m. here. I live in Vancouver in Canada. And I've been working with Oracle databases since Oracle 7 in 1998. I'm a database consultant since 2002. I have my own website, go to dba.com. I have a technical blog there, but not only, I have all kinds of different resources and presentations as well. I'm part of the Oracle ACE program. I was promoted to Oracle ACE director. I think it was at the beginning of this year. I just lost track of the last couple of years. I'm also involved with the community. I'm the president of the BCOUG, the British Columbia Oracle User Group here in Vancouver. I have a semi-technical podcast with Jim Suprinsky, if you know him. And we are talking about the tech world, but not technical stuff. So all kinds of stuff around the technical world, soft skills, interviews, diversity and inclusion, all of this. So if you like to listen to podcasts, just open your podcast app and look for us Beyond Tech Skills. And I'm part of the MASH program, which Erik will explain in a couple of minutes.
Okay, well, this is me. And as you can see, I have less to show off. The slide is a bit more empty. I'm a developer and self-employed since 2009. I'm an Oracle ACE. The oldest version I have ever worked with Oracle was the database Oracle 5. And yes, I am also part of the MESH program. And now you're probably wondering, what is the MESH program? Well, MESH is short for Mentor and Speaker Hub. What we intend to do with the MESH program is get more people to become a public speaker and share their knowledge. Now, we know that this might be a daunting step, so we would like to present people with the possibility to be hooked up with an experienced speaker. And that is what we do. If you think this sounds interesting, have a look at the website at that URL and look around what we do, how we do it. If it still sounds interesting, just sign up. It's absolutely free, no strings attached. If you ever think, no, I made a mistake, I don't want to be here, then just pull the plug, no problems whatsoever. All we want is more of you guys, you people, sorry, you girls as well, to step up and share your knowledge. Okay, now let's start with the real thing. This presentation has a theme. The theme is the Back to the Future movie. For those of you who have never seen that series of movies, it's about an inventor named Doc who invented a time machine, and about a young guy, Marty, who goes back in time and then struggles with getting back to his own time, back to the future. Within this presentation, we will give you a lot of examples about analytic functions, and we will try to implement the requirements first like you used to do it in the old days without analytic functions. And then we will show you how it's done with analytic functions. And we hope that you can see that it's better to do it with analytic functions. Okay, and what are analytic functions? Liron?
Yeah, so analytic functions, we know about row level functions, which, you get one row, one value or a couple of values from a single row, and then there is a calculation and a result for that row. And then aggregate functions are functions that work on a group of rows, but then return one value like sum or max or mean. Analytic functions are more unique in this regard. They are working, like they are calculated based on a group of rows, but the result set, the results for the function is for each and every row in the input. Okay, so if we have a few rows in the input and we operate, we run the analytic function, we will get a result. And the result will be for each row, but based on a group of rows. Okay, so that's the difference basically between aggregate functions and analytic functions. Because of that, we don't need to use the group by, and most aggregate functions have analytic versions, and we'll see that as well. So if we look at this example, you can see the table without the average. The right column is the analytic function. Okay, so we have the table with the ID, name, and salary, and then we have the analytic function, and we write the analytic function in the select clause, and it works for each and every row, but the input is the entire result set. So in this case, the average is the average of all of the salaries in the table. Okay, and that's why you see one average, like the same number for each row, but it's basically the average of the entire result set. And the analytic functions work after the group by or the where, or if you have anything else that's eliminate rows. So in this case, if we eliminated a few rows because of a where clause, because of something else, you'll see that the average of the analytic function is now a different number because it's calculated based on the rows that are left or remaining from after the group by or the where clause. Okay, but note that this happens before the order by. So after we execute the query, basically the where and the group by and all of this happens first, then the calculation of the analytic function, and at the end the result is ordered, and we'll see why this is important a little bit later.
Okay, well, which rows will be taken into account? How does an analytic function operate? Well, it uses the data from the other rows without a group by or without a self join, as Liron already explained. And as you can see here, the average for each row is calculated based on the entire result set. So each row will have the same average in this case, because the entire result set is taken into account. But you can also limit that in some ways. First of all, this is again the entire result set. Sorry, and you can also just make groups of data based on any criteria that you can think of. In this case, we have made groups of departments. Now, if you look at the row with beta near the bottom, then you will see that its average is calculated based on all the salaries within the same department as the one that beta belongs to. We can also limit the rows within the group that we are looking at. In this case, we look at all the rows within the group. Again, in this case, all the rows within the result set from first to last. But we can also, for example, look at only the current row and all the rows preceding that, all the rows that came before the current row. We could also just say, well, let's look at all the rows from the row right before the current row until the second row after the current row. In this case, Marlowe's average is calculated based on these 4 rows, and Landry's average is based on another set of 4 rows, namely the one before it, beta, until 2 after it, O'Connell. We can also even say, look at rows that does not include the current row. In this case, we look at rows from the third one before the current row until the row just before the current row. There's a lot of flexibility in this, in determining which rows to take into account for your analytic function. Okay. This is the syntax that we have to use when you want to use an analytic function. You start with the analytic function itself. Now there's quite a list of analytic functions. On the left, you will see a list, but it's only a partial list. Some of them are very common that you will see often. Others you will probably never in your career see. But there's a long list. Once you get the hang of analytic functions, have a look at the list and see what works for you and what doesn't. After you have typed the analytic function, then between brackets you can enter some arguments. They are optional, but some analytic functions require arguments. Then you have the keyword over, and that is a giveaway that you are dealing with an analytic function. If there is an over clause, over keyword, then it is an analytic function. If it isn't there, then it is not an analytic function. And then between brackets, there's the analytic clause. It looks mandatory, but as you can see when we drill down into it, that it consists of 3 clauses that are all optional. However, again, some functions require an analytic clause. It starts with the query partition clause. Now that is the part where we split the groups, split the result set up in groups like we did before on the department, but you can use anything. And as you can see, it's a partition clause. The keywords are partition by, not group by. Then it's followed by an order by clause. Note that this is the order for the rows in the result set for this analytic function, only for the processing by this analytic function. It has no effect at all on the order in which the rows will be delivered by your query. This is just for the processing by this analytic function. After the order by, we have the windowing clause, and if we drill into that, it looks like it's suddenly getting very complex. But if you look closer, you will see that there's a lot of repetition in there, and it basically comes down to first defining whether you're looking at rows or ranges, and we'll get to that later, and then telling it where to start and where to end, and it gives you it defines the rows that are taken into account. So could you show us this in some real code?
Yeah, of course. Okay, so let's start with the order by clause. So in this case, we have a table with salaries. We eliminated all the other columns. It doesn't really matter. And we'll take the row number analytic function as an example. And row number is similar to row num in Oracle. So basically, it's gives numbers to each and every row on the result set based on the location. Okay. Row number requires order by. So in this case, the over is order by salary. So just note that the result set is not ordered by. Okay, like Erik said before, the order by is internal to the analytic function. Okay, so in order to calculate the row number, it will order by salary, but the result set itself won't necessarily be ordered by salary, or might be ordered by something else. So when we order by salary, the smallest salary is 500, and this is why 500 will get the row number 1. Okay, the next one is 900, and that will be 2, 3, and so on and so forth until the end of the result set. And notice, because of the order by is internal to the analytic function, this will be the order of this output always. It doesn't matter how I order by the query, like the order by after the from, where, and order by. It can be different. It can look different because I order by the result set in a different way, but the row number output will always be the same because it's calculated based on the order of the salaries. Okay, so this is how row number and the order by clause work in analytic function. The next one is partition by, and Erik showed that before. We can take the result set and split it into subgroups. So in this case, the over clause is partitioned by department, and we see that we have 3 departments, 10, 20, and 30, and the analytic function is count star. So what we'll see is basically count of the rows per department. But as I said at the beginning, we will get that for each and every row of the result set. So it will look something like that. Okay, department 10 will have the count of 5, all the rows in department 10. Department 20 will be 3, and department 30 will be 1. And again, you can order by the results, the result in any way you want or manipulate them. As long as this is your result set, this will be the output of the count star analytic function. The next clause will be window, and this is a little bit more complex, as Erik showed you. But what we'll do here is we'll look at the over clause. So first of all, we order by salary, and then we take the window, which is rows between one preceding and one following. So basically, and the analytic function is average. So basically, we're calculating the average salary, and for each row, we take one row before and one row after, and we calculate the average of these 3 rows, the one before, the current row, and the one after. Okay, in this case, the table, the output that we see on the left is ordered by salary, and this is only for convenience because it's much easier to explain that way, but it doesn't have to be. Okay, in any way we can order the results that in any way we want. The results will be the same, just different order of the columns. So the first row that we are going to calculate is the one with the 500, and we're going to take the one row before, one row after, because this is the first one. Obviously, we don't have a row before, but the average will be on the current row and the one after, and it will be 700. For the second row, the 900, this analytic function will take one row before, so the 500, the current row, and one row after. So the window will always be 3 rows except the beginning of and the end, where we don't have a row before or row after. And it will be calculated based on the rows before and after for the entire query. Okay, so this is the concept of window. For each row, we make a calculation based on the rows before, rows after, and Erik said that we can take any number of rows or before or after, or whatever we want to calculate. So this is the rows keyword. And there is another option to do a window by range. And the concept of range is actually looking not on the number of rows, but the value of the row. So in this case, we take the same. No, it's actually a different query, different data. But we take the table here, and what we're going to do is calculate the average. Same thing, ordered by salary. This is why we ordered it here to have it more easy to read. But now it won't be rows before and after, it will be range before and after. In this case, we take 200 before and 200 after, meaning we look at the current row, we calculate the value of minus 200 and plus 200, and this would be the value, the window that we're going to calculate the average on. So in the case of the first row, the 1000, we don't have before, we have 200 after, that's 1200, and the average will be calculated based on these 2 rows. But when we go to the next row, we calculate 1200, basically 200 before is 1000, that's the first row, 200 after it's 1400, and we have 2 rows with 1400, both of them will be taken into account. So basically here we have 1200, this would be the row that we write the output, but the calculation will be on 4 rows from 1,000 to 1,400, and the average will be 1,250. The next row is 1,400, 200 before is the row with the 1,200, 200 after is 1,600. We don't have 1,600, but we have 1,500. Sorry, 1,500. So this will calculate the average on the entire window of 5 rows, and the average will be 1,400. And this will be the same, like be calculated in the same way for the entire table or results. Okay, so this is the difference between rows and range. And very, very important to remember that if you use order by, and this is relevant only if you use order by, if you don't use order by, the window clause is irrelevant. But if you use order by, there is a default window clause, and the default is range and not rows, between unbounded, meaning the beginning of the partition, and current row. Unbounded preceding, sorry, the beginning of the partition and current row. So if you use order by and you don't understand why things might look a bit weird, remember that this is the default window. If you want something else, like the entire partition, which is unbounded preceding and unbounded following, you have to write that specifically. Erik, back to you.
So when or how do you use these analytics functions? Well, where? You can only use them in the select and order by clauses. As Liron said before, you cannot use it in a where clause. And that makes sense basically because the analytic functions operate on the result set. And before the where clause is executed, your result set is not finished yet. So the analytic function cannot do its work. So it cannot operate within the where clause. And it can't be nested. So you can't take the outcome of an analytic function and use it as the input for another analytic function. There are ways around that, basically doing it in a subquery or in the with clause and then work on the result of that. And we will see that in the examples. But out of the box like this, without subqueries, you cannot use it in the where clause and it cannot be nested. And what are the benefits? Why would we use analytic functions? Well, most of the things that you do with analytic functions, if you would do that without analytic functions, it would require multiple times accessing the same table. And with analytic functions, you can do that in one pass, just one table access. So you will get a performance benefit. And apart from that, your query becomes a lot more readable and a lot more maintainable. Of course, if you understand analytic functions, because if you don't understand analytic functions, then your query will only be less readable and less maintainable. So I hope you pay attention, and after this presentation, you will understand analytic functions. So let's go to the examples that we've been talking about. We will present to you some requirements and then try to implement these. First one is for you, Liron.
Yeah. Okay, so the first example we'll see is the first value, last value. We're going to see only first value, but last value is basically the same concept, and you'll get it pretty easily. Okay, so the requirement is that we want to have a table. We have a table with employees' information, and we want to see for each employee the person in the same department who earns the most. Okay, so if we look at the result set, it will look something like that. And if you see department number 10 has only one person, but if we look at department 30, for example, we see all the people from department 30, but on the right-hand side, the two last columns, we see the high salary in this department and the person who earns the highest salary in this department. So basically for each and every person in the department will see the same result, obviously, but we'll see all the information about the people and the person who earns the most. So Erik, how would Doc do that without analytic functions?
People select Liron from Joule. He's the one who earns the most. So.
I wish.
Okay, no, serious. Obviously, we have to first find out what the highest salary per department is. So we go to the employees table, group by department ID, and get the max salary for that department. Then with that information, we can go into the employees table again and find the employee data of the employees that earn that highest salary. Once we have that, we can join it to the employees again, so we can get the list of employees combined with the information about the person that earns the most. Well,
right.
It's not too hard of a query, not too much to do. It's a pretty simple query. It's doable.
Yeah, it's relatively okay.
Yeah.
But there is a better way.
No.
Yeah. So if we take the first value analytic function, the first value analytic function means that we have an order by. We have to have an order by of the result set, and once we have the analytic function with the order by, first value means take some column, and we can take any column from basically the first row in the group if you have partitions, or from the entire result set if you don't. So in this case, we'll have the over, which is the analytic function part, partitioned by department ID, because I want the highest earner per department. So partitioned by department ID, order by salary descending. Once we have that, the first row will be the person who earns the most. So we'll take this analytic function twice. Once the first value of the salary, which will give me the salary from the first row, and because of the order by, this means the salary of the highest earner. And in the second time, we use the first value of first name and last name. So we get the first name and last name of the person in the first row of each department, and because it's ordered by salary descending, that would be the person who earns the most. And once we have these two analytic functions, we can build the entire query, which is relatively easy. Select whatever you want, and these two analytic functions, one is the highest salary, one is the highest salary earner or person, and then from employees, and you can order by, you can do whatever you want, and that's it. Much easier.
No, Doc is impressed.
Yeah. Let's see the next example.
Okay, in this one, we will show you lag and lead. And the requirement for lag, we have a list of orders, and we want to know for each order how long it's been since the previous time that same customer ordered something with us. So we can have an idea of how often the customer orders stuff with us. So the result would look something like this. As you can see, list of customers, list of orders with an order date. Each customer has a first order, of course, and that one does not have a day since the last order, because there is no last order, not a previous order. But all others for a customer will show the number of days that it's been since the previous order. How would we do that, Doc?
So Doc would do something like that. We'll just, okay, we have the orders table, right? So we'll take that twice, self-join. One of them will be the current orders, one will be the older orders. And once we have that, we'll group by customer, and we'll get the most recent older order date. So basically we have the order table, which is the current, and the self-join will be from the table in the self-join, the older orders will get the rows, like the maximum order date that is lower than the current order. I hope people can follow, and that will bring us two rows, one from the orders, one from the older orders, which are exactly one after the other. Okay, and once we have that, we can just subtract the order date, and we'll have the number of days.
Okay. I think this is just about as complex as the time machine that Doc has invented.
Yeah, it's not easy.
I think it can be done simpler and more efficient. So
I'm sure it can. So how? How Multi would do that?
If we go to analytic functions, then let's start with over. We partition by customer ID because we want to know the data within a customer, for a customer. So we partition by customer ID. Then we can order by order date. And if we do then use the lag function looks at rows before the current row. And by default, as it's used here, it looks at the row just before the current row. And we can get the order date from that row. Here we have the order date from the row just before the current row. Now we can just use this in a calculation with the order date of the current row, and we have days since the last order. And if we execute this, we get the result as we wanted it.
Yeah,
it's
awesome.
that easy. And if you look at the explain plans, the execution plans, this would be an execution plan for what Doc has proposed. And as you can see, we go to the table twice and then do a join. Whereas the other query has this as an execution plan where there is only one table access. We do a window sort for the analytic function, and that's it.
Yeah.
So this is more efficient, and it's also simpler.
Right. And this is for this query, but I remind you, Erik, that in the last example, we had to access the original table 3 times. So exactly. The execution plan would be even worse, and the performance obviously as well.
Exactly.
Okay,
let's look at the counterpart of lag. It's lead. Lead doesn't look at the rows before, but at the rows after the current row. And here I have a different requirements for all kinds of actions. We have statuses. An action can at any time at any moment in time only have one status. So there may not be overlaps or gaps in the status validity. Would look something like this. Action IDs that have different statuses, and as you can see, there is never an overlap in the start date end date within an action ID, and there is never a gap. So how would we go about ensuring that we will never have overlaps or gaps?
Okay, so what I would do, or what Doc would do, is we'll take a table with a start date and end date column. Okay, and then once you insert a row, we'll have a trigger that if there is a previous row for the same action, we set the end date of that row when we insert the new row. Yeah. But it's a bit tricky. You need to watch out because it's a mutating table. The trigger actually queries the table that it's changing. Okay, so we need to be careful there. But also, if we update or delete rows, we also need to adjust the end date of the previous rows. So we will have an update or delete trigger as well to fix all of that. So we won't have gaps, or we won't have anything that is, not like bad in data wise. And that's a mutating table as well. But yeah, that's possible. The problem with this concept is that once you rely on triggers and something like that, we just need to pray that nobody will disable these triggers, or mess with that, so we can be safe that the data is correct. And that always works, right, Erik?
Absolutely, absolutely. I've never ever seen this go wrong. Absolutely, this is triggers are always enabled, so that's no problem.
Yeah,
of course. Well, what I would suggest in this case is to just have a table with a start date without an end date, because the end date will basically always be equal to the start date of the next row, right? Right, because you won't have gaps and you won't have overlaps.
Right.
Now, if we do that, sometimes we do need to have a start date and an end date, because we want to know is this row valid at date X.
Mm-hmm.
For that, we could use a view that does this. We use the lead analytic function, which looks by default, as we use it here, to the row just after the current row. By doing lead start date, you get the start date of the row just after the next row. We will call that end date, and if we run this query, then we have the start and end dates together, and we know when we have the information that we want. And we don't have any triggers. We don't have all this complexity. We don't have to pray. We know that there isn't a gap, and if we ever delete something or insert something, everything will be updated automatically.
Yeah, and Doc is impressed.
I have to say, this is not always the solution if you have a start date and end date, but it does show you what you could do with the lead function.
Right, and also if you use a view to do that, you obviously can create a view with a self-join without analytic function, and not use the triggers and stuff. But we just wanted to show different approaches for the same problem. And again, if we use self-join, we can do that. The performance won't be that great, and the code would be much longer.
Exactly.
Right?
Exactly. Okay.
Yeah, the next example. So rank and dense rank. So our requirement is that we have a table with the results of Olympic contest. Okay, and we need a query that calculates or shows the podium with the winners. So we need first place for gold medal, second place for silver medal, and third place for bronze medal. So this data was taken from Rio 2016 from 100-meter freestyle swimming men. So as you can see, the Australian guy got the gold medal, the Belgium got the second place silver medal, and the American got to third place with the time. So Erik, how would Doc just take the table and present only the podium?
Well, it couldn't be simpler. I mean, this is just, you take the table, you select the stuff, you order it by time, and then you just select the rows for row num less or equal than 3, or maybe even just fetch first 3 rows only, and you have your top 3. It's as simple as that.
Right. Not even, self-join.
No, nothing at all. Just
so that's awesome. Simple. So what is the problem? The problem is what happens if two swimmers got exactly the same time? What happens if 2 people need to be on the podium at the same spot? With your query, if we have a tie, Oracle will randomly choose one of them. Like in this case, Peter and Nathan, the Belgian and the American, got exactly the same time. So with your query, Oracle will just randomly choose one of them, in this case, Peter, the Belgian, and that one will get the place number 2, the row number 2, which is the silver medal, and the other one will get bronze, even though they should be the same time and the same spot in the podium, right?
Yeah, but if you have this, then you just should get a better stopwatch or have a photo finish. This is ridiculous. But
yeah,
anyway.
maybe we should go to the store and get a better one.
Okay.
But if we need to solve that, that would be tricky to solve with row num,
Yeah,
right?
Absolutely. This would be tricky. Yeah, absolutely.
So the way to solve that would be, surprisingly, analytic function.
Oh, never would have guessed.
So we'll take the rank analytic function, and the rank, as you can hear by the name, it's ranking of rows based on their location. So it has to have order by, and in this case, we'll order by time, and we give each row a rank. Okay, so in this case, as you can see, both Peter and Nathan got the rank of 2, meaning Kyle, the Australian guy, will get gold medal, and both Peter and Nathan will get the silver medal. We don't have a bronze medal here, and this is actually by the Olympics rule. So if you have multiple people on one spot, the total of people that are on the podium should be 3. So I don't know what happens if you have 3 people on the same spot, but that's a different story. So in this case, we'll have 1 person with the gold, 2 people with silver, but no bronze. Okay, and as you can see, the rank analytic function supports that, because the next one, the Canadian Santo, will have will get the 4th place. Okay, so as you can see, 3 is not here because once we have a duplicate or the same place, the same rank, the next one will skip basically based on the number of rows. So the guy from Canada is at the 4th row, so he will have the rank of 4, and 3 will be skipped because we had a duplicate 2. Okay, so basically this is how it works, and once we cut the first 3 rows, we'll get exactly what. Actually, we don't cut the first 3 rows, we cut up to place number 3. We'll actually get the podium exactly as we want to. But what if we do want to have bronze as well on the podium? We just change the same query exactly, we just change the rank to dense rank. And the concept of dense rank is that even if we have duplicates, the next row will get the next number. So in this case, if we take up to including place number 3, value of 3, we'll get 1 person in gold medal, 2 in silver, and 1 in bronze. So Santo, the Canadian guy, got up to number 3 because it's a dense rank and we don't skip numbers. So we've got 1, a couple of 2, and then 3. And if we have duplicates, again, after the duplicate will be the next number. While in rank, we'll skip the number based on the number of rows that we had duplicates. Okay?
Okay.
So this is rank and dense rank. And let's move on to the next example.
Okay, and I think we're going to have to speed up a little bit because we are almost out of time. So in this case, max min, I want to know for the IT and the finance departments, how much every employee earns more than the lowest salary in its department and less than the highest salary in its department. That would look like this. For example, Bruce Ernst on row 4 earns 6,000. That is 3,000 more than or less than the top salary in his department of 9,000, and it's 1,800 more than the lowest of 4,200. How could we do this?
Okay, so I think we did something similar before. We'll just group by the department ID, we'll get the min and max salaries. So now we have a list of departments with the minimum salary and the maximum salary. We'll have this in a with clause. So we have a department extremes view, quote unquote. And this is the result for each department. We'll have the minimum salary and the maximum salary. And now we take that, we'll join that to the employees, and we just calculate the highest salary minus the current salary and the current salary minus the lowest salary. Oh, yeah. And this is what we'll get. Exactly what what you wanted.
It's exactly what I asked for.
Right.
But I don't agree with the fact that it doesn't get simpler than that. I think it will get simpler than that.
Okay, let's
have a look at that. If you just use the max and the min analytic functions, and you partition by department ID, then you get the max and the min salary for the department that of the employee at the current row. So you can just subtract that from salary or salary from the max, and you get exactly the information that you want. And there are other aggregate functions like this as well, sum, count, average that we've used before. And you can just use it like this.
Yeah, and we saw the first example, we saw the first row and the first value, last value. And basically you can do the same with first value, last value, or max and min. But in some cases, you'll have to use one of them, right?
Yeah, correct. Okay. This one, our company is growing. We get more and more customers. So our job that runs at night and creates the invoices to be sent out runs longer and longer. So we want to split it up in 10 sub-jobs that will run concurrently. So we have to determine which job has to do which 10% of the invoices.
Okay.
On the left, on the lower left, you can see that the table has an invoice ID, a customer ID, and a ready to send. If the ready to send is set to yes, then the invoice has to be generated at that night. Okay, how could we do that?
Okay, so I just need to split the table to 10 different jobs?
Yes.
Yeah, okay, you know what? I'll just use row num and modulo. So basically, modulo row num and 10 will give me the remainder between 0 and 9, and that would be exactly my job. So we'll do something like that. Select ID, modulo row num, comma 10 from invoices, and this is the result.
Oh, looks good. Simple, great. Yeah, fantastic. However, we tried this, and yeah, it's faster, but it's not as fast as we wanted or expected. And that is because IDs are generated in sequence. And so a row for invoice number 2 is created after a row with invoice ID 1. And so they will be physically stored together in the same block. So now, the way you did it, row 1 goes to job 1, row 2 goes to job 2, row 3 to job 3.
Yeah, this is how modulo works.
Exactly. And all these jobs will be looking at the same blocks. So they will be competing for this IO. And that slows it down. So what we would rather have is...
Yeah, just a second. Just one comment. What happens if all of the ideas ended with 7? Like 7, 17, 27, my solution would not work like completely.
Yeah, exactly.
Right?
Exactly, that too.
Yeah, I trusted that we have all the numbers, which is not always true.
Yeah, but it's the chance of that happening is not that big because, like I said, we have a lot of invoices. Otherwise, we wouldn't have to split it in 10 sub-jobs. So the chance of that happening is not that huge.
Right.
But it could happen.
It could happen in some other, system with the specific data.
Exactly. So what we want is job 1 to just do the first 10% of the rows and job 2 the second 10%, etc. Like what you see on the top right.
Yeah, okay.
So how would we do that?
Yeah, that would make more sense, but that's a tough one. Okay, let's try. So basically I need to count the number of rows. I need to divide that by 10, and I might have a remainder or leftover, right? So I need to figure out which one or how many we've got. And then the whole number I can split up to 10 jobs, but then I need to spread the leftovers to the first jobs. So if I have 3 remainings, one will go to job number 1, while one will go to job number 2, and one will go to job number 3, right? But once I do that, I can take the entire result set, order by ID, calculate where the cutoff is. Once I have the number of rows per job, just calculate where the job basically ends, like what is the maximum ID for each job. And then I can show it to you with the first and last. And it will look something like that.
I'm impressed. Please really don't retire, because we need you to maintain this code, because nobody will understand this.
I'm not sure I would be able to maintain this code.
Okay. So let's try to make this a little bit more simple, a little bit simpler.
Okay, let's try.
We can just do this. There's a function entile, which will do exactly what we want here, because entile takes the rows and divide them into buckets, as it's called. And it will assign a number to each row that indicates the bucket that row should be in. Entile will expect one argument, in this case 10, and that is the number of buckets that it needs to create. And we order by the ID, because we want the stuff to be in various jobs according to the order of the ID. If we run this, then after this job ID has been assigned to each row, as you can see here, then we can just group this. Yes, next slide, please.
Sorry.
Then we can just group this by job ID and do a min, max, and count. And if we run that query, then we get this result. And that's exactly what we needed. And this is a lot simpler query than the one that Doc came up with.
Yeah, much easier to maintain as well.
Absolutely.
Yep.
Yeah.
Sounds good.
Okay, let's go to the last example.
Yeah, we have a few minutes. Good. So let's combine that. And I know it sounds like a weird requirement, but this is based on a real story, actually. So I want to take the 3 largest departments. Okay, so again, I have the employee table. I want to take the 3 largest departments with the highest number of people, just the 3 of them. And then for each one, present the 2 people who earn the most in this department. So in total, we'll have 6 rows. Okay, 2 people, 3 departments. Okay, how would you do that?
Well, first of all, we have to determine which departments are the largest. So we have to do a query again and group by department, and then find out how big they are, and then get the top 3 of those. That isn't too hard. But then for each of the departments, we have to find out which are the top 2 earners. And that means going back into the table again with a subquery for each of these departments. So that requires a subquery for 3 departments or 3 self-joins. And if next week you decide that you don't want it for 3 departments, but for 10, then we are at 10 subqueries or 10 self-joins. And I would probably pretty soon skip to PL/SQL and just do it in there to have it a bit more flexible, a bit more generic. But yeah, that's not what we want either, because we want it in SQL, of course. So yeah, how could we do this in a more elegant way?
Yeah, so this is a bit more complex, but still very doable in analytic functions. So basically what we need is to find the departments, the largest departments, and the two people who earn the most in these departments. So we'll use the analytic functions, count star, and partition by department, and we'll call that department size. So now we have for each row in the result set, we have for each person basically the number of people in their own department. And also we'll create another column based on the analytic function row number, where we're going to partition by department ID and order by salary descending. And we saw that at the beginning, I think, with the first row example. And this would be the salary rank, okay, row number. So now for each person, we have the number of people in their own department and their own rank based on the salary in their department. Okay, so we just added this value, these values. And now we're going to use that as an inline view. And Erik said at the beginning, if you remember, that we cannot nest analytic functions. So this is basically the way we do that. We do an inline view. We get the department size in this case, and we use the department size inside a different analytic function. So here we'll take a dense rank and we do over order by department size, and we call that department rank. So now we have the rank of the department based on its size, as well as the salary rank of the person inside the department. And once we have the department size, department rank, and the salary rank, we have all the information we need, and we just, choose to view the rows with department rank less equal to 3 and salary rank less equal than 2, and we get exactly what we want to.
Yeah. And as you can see, this is an example of using, as you said, one analytic function within another by using a subquery, but also an example of using an analytic function in the where clause by using the analytic function in a subquery.
Right.
Yeah. Okay.
And that's it, right on time.
Yeah, we're done. Okay, then it remains to answer questions if there are any.
Yeah, and thank you for joining us.
Yeah, thank you very much. Well, the Q&A for now is empty. So
yeah.
Okay, it seems that there are no questions. Then I think we are done.